tracking mount. Like basically that's unique, and I haven't seen anything really like it. So the motivation was, for us, is basically what happened was most roof mount systems have to be fixed because and most of the ones that are dynamic and move are always on with single axis failure. You always have to issue, then you have them blown off, and you have to issue, and it's not generally safe practice to put them on roofs. So our idea was to make a roof mount system that's capable of basically withstanding these tolerances and providing the same services as a traditional ground mount system. Andrew, would you go over question?
So the project summary, we're fitting a panel that will increase the efficiency of basically the panel will rotate based on the sensors, and it will make using the sun's energy more efficiently. Because we're having a mount that's already being made by us, it's going to make easily installation for people who are trying to use this device. We're going to have an innovative hydraulic design system, which will basically have light sensors to sense the sunlight and adjust basically towards the sun so that it maximizes output. So once completed the project, it should provide the customer with data which can be used for analytical purposes.
Alright, so let's go a little bit more in depth. I know we introduced that, but prefer to get a little bit more in depth. So I'm the project lead. I'm a computer engineer. I have a strong background in embedded systems. I worked in manufacturing for about 3 years of my life. I have a free product, full products, some credit to my name. And now, since we lost a member, I'm now in charge of hardware as well as this embedded system firmware.
I'm Timothy Hausler. I am a computer engineer, and I'm in charge of the algorithms for this project. I'll be taking the sensor data and converting it into the positions that the solar panel needs to be in, as well as extrapolating further data for larger scale movements of the solar panel.
I'm a senior computer engineering major, and I'll be in charge of the Android development. We'll be having an Android app that will act as a user interface where you can see where the sun is at the current moment, and a lot of times with the sun not being able to accept the input of the sun, maybe there's some clouds in the way, we have geolocation data that will also come into the app and help adjust the solar panel to where it needs to be.
Okay, so during our summary, we explained that we want to have a solar mount system for the roof of a building, and that's not fixed. Currently, there are several types of solar panel mounts. There's pole mount systems, ground mount systems, roof mount systems. With ground and roof mount systems, you're looking at a fixed system that has very minimal tracking capabilities. Pole mount systems have fixed position, and dual axis tracking, and single axis tracking, which significantly increases the efficiency of the solar panel. So we were wondering, why is it that roof mount systems are only limited to fixed positions? Through some research, I found that at the very most, we're looking at single axis tracking, where on the roof of a building, a solar panel can angle towards the sun, but only on a single axis. What we're proposing is take a roof mount system and give it the ability to do dual axis tracking and to significantly increase efficiency, as well as increase performance of the overall system.
Alright. Our working requirements was that they had to be easy to install, really high efficiency, and basically reinforce the benefits of solar power to people. Because once you get fixed mount systems, they're not as efficient, and you're kind of throwing money down the toilet at that point. The engineering requirements is that it would be able to stand 30 mile per hour winds. The system had to be around 3 degree in air because solar radiation, you don't have to be 100% precise. And basically be running 24/7 and be able to come back from a failure. Our proposed approach, like Tim said, was basically we have a unity hydraulic system which has 5 points of failure. So basically what happens is you have a hydraulic actuator here and here, and it pushes the panel up. So the panel itself is sitting flat at default position and gets pushed up and pushed around, and the center pulls a ball and socket joint. So we tracked we'll have two quick methods of tracking, which would be LDR sensors and geolocation. So over here we have a block diagram of the control system. Here I have the embedded controller which is a Raspberry Pi connected to a Bluetooth module, and the Android phone will send its geolocation data over to Bluetooth, and embedded controller will send power data back to the Android phone when requested. The plug-in board up here is an essential component because it controls all the analog control circuitry, as well, and does all the AD processing as well, and controls the signals from the embedded controller to the stepper motors. Alright, here's a little bit more of the detail here. You can see here it has Euro connections to Bluetooth, outputs the control signals to PC, the plug-in PCB, and creates data for the power meter. So I'll take a couple of these modules here and explain a little bit more in depth. We have stepper motors, we have and solar tracking modules. The Android phone will have a UI basically that will where you can it will send power data and all that. Alright, the embedded controller we chose is Raspberry Pi. It's relatively cheap and it fulfills our needs. Basically a mini computer, and it runs really well. And the Bluetooth module is HC06. It's an RS-232 standard serial Bluetooth connection. It's low power, uses 30 milliamps, and it's about 30 foot range. Plug-in PCB, like I said before, very essential component. Does all the analog signal processing, and it controls the control signals to the stepper motor.
Okay, so for the risk analysis, obviously, in any project, there are a lot of risks that can be handled, but we were wondering, should we complete this project with a given budget, and we've realized that we can, some other risks that involve network failures. Will the Sun tracking algorithms work correctly the way we want them to? And, do we have enough time, and could the hydraulic actuator, supply enough force to rotate this panel the way we want to? And we believe that all of these things, they may give us some issues, but we will be able to tackle all of them.
Okay, so through our project, there's going to definitely need to be some testing that needs to be done. The components we need to test are the actuators, the sensors, and our embedded system, as well as communication with the Android app. With our testing, we want to isolate every part to make sure we know that it's working. And with the actuators, we want to have a shunted system so that we control the input into the motor, that will raise and lower for what would be the solar panel. Well, for the Bluetooth module, we want to send data from the app to a capture point and make sure the data we're receiving is actually there. And we'll be following the same procedure for every device. It slowly will move on to integrating and performing similar unit tests. So with the actuators, we combine it with the embedded system and then send dummy data from the embedded system off to the actuators and so on.
Alright, here we have our bill of material and cost estimation here. As you can see, we had a pre-approved budget of $381 from the department, and we managed to achieve that here. Here we have the rack and gear system that we'll be using instead of hydraulic actuators due to the fact that we need to scale this down. This project will not be creating a market-ready project, but will be more of a blueprint for actual product. Not to mention, we also will be conducting a study which will show its efficiency compared to traditional systems.
So with the timeline, we're skipping ahead past all the proposal stuff and getting straight into the research and development. And for the research, we've been looking through different actuators that we can use, which is where our cost analysis came from. And once we finally decide on the actuators, they'll be purchased, and we'll move on to the circuit design for those parts. But following that, or parallel to that, we'll have our app and algorithm development going on. And currently, Andrew is moving on to alpha with his app, and my algorithm is beginning to move into the coding stage. Once we finish the software and app design, we can start integrating all the parts of the system. And hopefully, sometime in late January, early February, we'll have a working system, and we can begin testing for proof of concept.
Alright, this is our feature timeline. This will be happening over break and into early next semester, so we can have the time to conduct our study. First, we're going to test the embedded software and test the Android software with a fully integrated system. After we do that, we'll start developing the actual physical framework for the panel with all the racking gears and all the mechanical engineering components to it. And that'll take about a month or so. From there, we'll actually we'll construct design, and we'll have a fully integrated product that we can be testing and preparing to traditional systems. So our work so far, I implemented UART code for the Raspberry controller. I'm still working on the GPIO mapping as well as the serial connections. Android app is in alpha, and the vector mapper position is nearly complete. For the hardware, I have a Bluetooth module that's fully integrated, as you can see down there, to the Raspberry Pi. And the solar modules are finished, but I'm waiting on the analog control board to test those.
Okay, so for the Bluetooth application, the Android platform implements a lot of APIs that are, that we would be using for the Bluetooth, because once the Android application will be using Bluetooth to connect to the Bluetooth module, it's going to, do the few main things that it has to do, which is scan the devices, then it has to connect to the device, and then transfer this to the data.
Okay, so I'm just going to go through this quickly so we can wrap up. With our algorithm, there's going to be a need to calculate the normal vector of the solar panel so that we can reverse it to get how high we need to have our solar panel set up. So this is going to look like a mess, but all these numbers make sense. Since these numbers down here are the outer edges of the base of our solar panel, this is the base of our actuator, and the top is the actual solar panel. Well, using our algorithm, we can provide just the length and the width of the base and the actuator heights to get the normal vector, and then we can reverse that back to get the proper actuator lengths to point the solar panel directly at the sun. And compared to the last slide in this one, you'll notice that H on the second block of numbers has changed to a 5. That rotated the solar panel from being on an angle to being perpendicular to the base of the plane.
Alright, we're ready to discuss future work, so just to go into the summary, we're creating a new unique concept for smart solar panels, and we achieved approximately 40% of our project goals. Any questions?
I think you have an incredibly good marketable idea. I suggest you speak to solar companies in the state, especially. I'm concerned about the use of hydraulics to move the solar panels. I'd much rather see you use some electrical current from the solar panel and drive a DC motor or something like that.
Yep.
You can figure that out. And I'm curious why you chose 30 miles per hour as a constraint, when if I was a homeowner and I heard that, I'd be like, nah. I see 50-mile-an-hour winds up every full time.
Well, to be honest, that was a little bit more of an arbitrary choice. It was kind of, but to be honest, we're going to probably build a stronger system that withstand 30 miles per hour, but that's more baseline based on regular occurrences and like all that. So basically, they should be able to have a strong tolerance, like probably to up about 80 plus for short periods of gusts, but 30 miles sustained. Yes.
This may be beyond the scope of your discussion, but any idea how scalable this is? How big an array you can
Well, actually, each individual module can be daisy-chained together power output-wise. So each module will have its own. All these modules can be just linked together.
So modules will be individually controlled? No. A whole large array of modules will be.
Yes, and they'll all be doing their own solar tracking based on their input data. Yes.
Is this designed for flat roofs?
What can happen is we have an idea for two types of frameworks. We're going to have probably the bottom framework can be bendable, based if you need a pointed roof mount or a flat roof mount. And we're going to have this sitting on top of that base framework there, rotating around on the flat surface.
If you're talking about one solar panel, that's one thing. If you've got an array of them, you should look into the geometry when you start rotating them. Just because they may interfere with one another.
Yeah, that's spacing is a little bit concerned with shadow overlay, but that's also when you have an array of solar panels, that's usually, especially in solar farms, that they compensate for that based on spacing. Yes.
Does your system have, like, is it required for any standards that you guys are going by? Like any requirements?
Well, right now, since we're not actually making a market-ready product, right now we're just doing the basic framework for it. We're not really too concerned about having 100% standards because we're in limited budget scale. But this is like more of a blueprint for future product development. Yes.
You said you're making an Android app, right?
Yes.
So I thought maybe if you could get some weather data from your phone, you could maybe get like an emergency setting. So if the winds are going over that 50 miles per hour, it can go flat to the roof and not, so you don't have to worry about it getting ripped off or the user forgetting that it's currently pitched at an angle or.
Well, that's the limitations though with the Bluetooth and range, is that the Android app is used for one-time programming, sends a GPS location data for calculations independent of the sensors, as well as basically retrieving power data when you want to go up. So basically, if like, oh, let's see how the solar panel's going, you go up to the roof, you connect to it, you hit retrieve power data, and it gives you all the power data that it has logged in the system.
So, okay, thank you.
Yep.
Right, I'd like to thank Mr. Wang for videoing these presentations. And hopefully we'll be able to do some debriefs and maybe have some fun with that. Who knows what will end up on YouTube, right? But I'd like to thank all to recognize again the Board of Advisors and the faculty for coming out, and other guests. And it's nice that when the students are better dressed than me. So, yeah.
So just a couple of closing remarks. First of all, I want to thank Dr. Jacos and all of you for the invitation to be here. I am absolutely blown away by all of you, your drive, your knowledge, and your presentation skills. Absolutely extraordinary. Any company that gets you will be proud to have you.
Amen.
Trust me. One of the things that makes me most proud in giving back to the school in the fashion that I do is one of my roles is to continue to remind the president of the college, the provost, where to spend money. Because I don't think they spend enough money in the engineering school. And so you make me very proud. And we in fact, when I walk into the building, nothing much changes, even my professors. So thank you very much for that. Extraordinary. Thank you.
Thank you. Thank you.
Thank you.
All right, George, you have anything to say?
I would like to thank the dedicated efforts of our students. The students did an outstanding job. Congratulations to them and to the faculty as well, to Dr. Corinne and Dr. Wang. Thank you.